Thanks again for attending this inaugural Arcis Symposium. As Graziella mentioned, I'm going to be talking first today, and I'm going to be discussing advances in AVO compliant and Azimuthal processing, and I'm going to be sharing the load with Peter Cary here. I'll start out by talking about AVO compliant processing in general, and then Peter will follow up by talking about a few of his innovations: unbiased surface consistent scaling and also phase and statics corrections. And then he'll talk about how you might apply these AVO compliant ideas and paradigms to converted wave data. And then I'll resume the floor after that, and I'll talk about processing azimutally, so AVO compliant processing in the context of azimuth preservation. So AVO compliant processing. Well, here are the various key steps which underlie or form the underpinnings of an AVO compliant processing flow. Noise attenuation, which is really the workhorse. I mean, frankly, battles are won and lost in processing in the trenches of noise attenuation. So we'll spend quite a bit of time talking about that particular topic. Also, refraction statics, residual statics, surface consistent processing, new ideas that we're bringing to the table, and those will be quite clear to you after we've done our talk here. VTI compliant NMO, operating from full surface, from topography. Pre-stack interpolation we'll talk about later on, and pre-stack time migration. So those are the main components in the flow. And of these, in the next few minutes, I'm going to focus on the noise attenuation, and we'll flirt a little bit with some of the surface consistent processing innovations and scaling also. Peter's going to come in later and talk in more detail about those. So let's talk about noise attenuation now. And actually, before I forget, Xinsheng Li did the bulk of the preparation of this talk, and really he could equally well deliver this talk as could Peter and me. So many thanks to Xinsheng. I'm very proud of the deep bench strength we have at Arcis. I don't mean to sound trite and insincere when I say that. We really have worked hard to get some top-notch people driving these things. So to talk about noise attenuation now, we're going to look at things in many different domains as we beat down noise in an AVO compliant fashion. And that's because we need to choose domains judiciously to ensure that the noise stands out in one domain or the other. And so we've got to be pretty open-minded and flexible when it comes to attacking the noise trains. So for example, ground roll is best attenuated in the shot domain. High amplitude sporadic noise, which exists in great amounts typically after decon, is best attacked either in the offset domain, so that means offset is frozen and you stride across, say, the CMPX and CMPY coordinates, perhaps ignoring azimuth or perhaps paying attention to it, and or the CDP domain where you stride across the offset coordinate and try to pick off noisy traces. And finally, for random noise, we really want to be in a domain where things look like the stack, where we're striding across, say, the inline and crossline coordinates. So the crossbred is one such domain we'll be looking at, and of course, so would be the post-stack, good old post-stack volume. So let's look at ground roll attenuation first. As promised, this is done in the shot domain, and this is just a representative example where you see an input noisy record, an output which somehow magically looks beautifully noise attenuated, and then the difference between input less the output. And it's important, as I'm sure you're all aware, to go plumbing through that difference and ensure that there is no residual signal present. So how do we get from here on the left to here on the far right? Well, there's actually quite an elaborate process underlying things, and don't worry, I won't be getting into the minutiae here in this discussion. But suffice it to know, the basic philosophy is to do some sort of preliminary noise attenuation, and it might be somewhat heavy-handed in the sense that it may have some problems in the sense that it might have residual signal present in its it may inadvertently remove residual signal, and so we have to do something after the fact to go fix that up. So in this case, this heavy-handed noise attenuation in the context of removing ground roll is simply a high-pass filter. So we just say, okay, well, all the low frequency stuff is noise. And obviously, intuitively, that can't be a good thing in isolation, because in the low pass stuff, the stuff we're discarding, there are obviously low Fourier components, low frequency Fourier components of the signal. So we've got to somehow add those back. And it's adding back that stuff that's at the heart of this flow. Basically operate on the low frequencies and try to identify and isolate just the low frequency signal and add that back to that high pass filtered result. So I'll show how that plays out. We isolated a single shot and studied it. So here's your input, and we basically do all this fancy stuff to get to this final result. So here, how do we do it pictorially? Well, here's that low pass I was telling you about, where we think we've got mostly pure noise, but you can see these hyperbolae, which are, of course, associated with low frequency components of the signal. So we can't have this in our noise model, right? We must add back that low frequency signal. So we do a bunch of stuff. We mute, we NMO. We apply a ground roll attenuation, a linear array forming technique to this, online to this data. And you can see from here, from the NMO step to the LAF step, there is a bit of improvement, but there's still all sorts of remnant noise. Then we do an outlier suppression, which is quite successful, and then an inverse NMO, and now we're assuming that we've got just good old-fashioned healthy low-frequency signal, which can then be added back to the high pass to produce this result. So that kind of circuitous flow is at the heart of all our AVO compliant processing. So it does give rise to very complicated job decks. As far as QC goes, I want to make an important point. Whenever we're doing this domain-specific noise attenuation, we of course look at the input, output, and difference plot in the domain at hand, obviously. But behind the scenes, we're also creating stacks, even if they're very preliminary stacks, to look at the result of applying the pre-stack process and stacking and comparing that to the stack obtained without said pre-stack process. So here's the stack before the ground roll noise attenuation, and there's the corresponding result after. And I'll just toggle back and forth. So there's before, after, and there's the difference plot. And it's just kind of a sanity check that in the final stack domain, which is of course very important for structural interpretation, that you don't have any residual signal present. But remember, the noise attenuation itself took place in the pre-stack domain. So we're going to move away from ground roll. I want to show a lot of real data examples. This is, as I said, an in the trenches talk. So we're looking at stuff that you may not normally see over the course of your project. We'll go into different domains, as I said. So in the context of post-deconvolution noise suppression, we have to worry about high amplitude noise bursts. And often the CDP domain is a really useful domain for identifying those bursts. So here's an example of a certain 3D CDP gather. There's the input. You can see these noise bursts. We apply a median style outlier detection, beat down the noise, and in the difference plot you see before you, there's no obvious specular signal reflection energy. So this is a careful example that we're happy with, and we would go forward with this as our post-decon noise suppression. We can similarly, and often after the fact, go into the offset domain for further noise burst suppression. I'm showing you one common offset volume, a specific inline from a 3D. This is unstructured data. We're mixing azimuths willy-nilly here, but for these unstructured data, that doesn't seem to be a big problem. All we want to do is get a domain where these noisy traces stand out, and this is a useful domain for doing that. So there's one offset volume before. There's the after and the difference plot where we've removed only noise and no obvious signal. But I'm going to go back and forth, before, after, before, after. Well, to be honest, I find this result a bit underwhelming for the reason that you can't see a lot of healthy specular reflections in that single offset volume. The fold is just too low, and there's obviously all sorts of remnant noise problems in these data. So I'm showing now the stack before applying this offset domain noise burst suppression, and there's the stack after. Remember, the noise burst suppression itself was affected pre-stack, and we just stacked it up. So there's before, after, and the difference plot. So again, those QCs are being employed all the time in our flows. And if we see remnant signal in this difference plot, we back off with the aggression of our parameters for the noise attenuation. I want to now show a random noise attenuation example. So this is the crossbred domain, and we're going to look at an FX. We typically perform FXY prediction filtering. It's actually an AVO compliant noise attenuation when it's employed in the crossbred domain. So there's the input, a certain inline, one fixed crossbred. A crossbred, for those of you who don't know, it basically it's a domain where it's pre-stack domain. For each crossbred, you get a single fold at each CMP, so you can think of it as like a stack volume in your minds as far as the indexing of the domain. So this is like one inline, but it's single fold pre-stack data. And there's the output after the prediction filtering, and there's the noise. So we'll just toggle back: input, output, input, output. So again, it's done a decent job. And again, I thought it would be useful to look at the stack and how does this FXY filtering in the crossbred domain manifest itself on the stack. Here's the inline before the random noise attenuation. There's the after, and there's the difference. There's the noise that's being removed. So input, output, input, output. So I neglected to say earlier that we decided to frame part of this presentation kind of with a philosophical bent. We view AVO processing as and it's a bit of a mouthful, but we couldn't come up with a better term. It's really a multi-faceted, iterative process. And well, before I describe the various facets here, I want to elaborate on this title. Basically, the issue, the reason you've got the notion iteration and a whole bunch of different facets or criteria or objectives is because any one of these things we're about to discuss, these things are best affected or employed after some of the other things have already been done. So in other words, there are interdependencies and contingencies among the various facets in processing. So to be a little bit more specific, this first facet here, the notion of converging the velocities and the statics, well, you can't really do that well unless you beat down the noise. On the other hand, beating down the noise, minimizing noise, requires good statics and velocities for optimal performance of some of the algorithms. Amplitude variation, minimizing amplitude variation. Well, to do that properly, you need to have the noise beaten down. You need to have the noise beaten down as much as possible to minimize the phase using existing algorithms, and so on. And you'll notice the verbs have been chosen carefully here: convergence, minimization, and enhancement. As we evolve and go through more and more iterations, we're expecting these processes to do less and less. And we're going to illustrate that now. First of all, we'll start off by looking at amplitude variation. So when we apply our surface consistent scaling, and Peter's going to talk in more detail about that concept, when we apply that stuff to the pre-stack data in the initial stages of processing, you get a lot of variation in the correction factors. So what you're seeing here is a map view of the receiver scalars. So these are the things we're going to take the reciprocal to correct for the surface consistent amplitude effects in the algorithm. But these are the scalars before we do that. And you can see this is done before decon. It's when we do our first pass of surface consistent scaling. And there's quite a lot of variation across the survey. Ditto for the shot scalars. Same thing, a lot of variation. Now, we move to the second iteration. This is after deconvolution and a bit of associated noise attenuation. And essentially, we do a second pass because we want the the surface consistent scaling algorithm to operate in a realm where its assumptions are better fulfilled. And we want, in particular, the noise to be beat down a bit better and the wavelets to be crisper. So we give another pass, do another pass, and notice that the distribution shows much less variation. So we'll toggle back and forth. So this is iteration 1, iteration 2, iteration 1, iteration 2. So as we're doing more and more of this surface consistent scaling, the algorithm's not having to work as hard. And it's kind of a sanity check. It shouldn't be working as hard because we should be getting the preliminary gross effects taken care of in the earliest iterations. And similarly, here's a third iteration further along the flow. So this is second iteration, third, second, third, and again, the variance, if you will, of the actual scalar magnitudes is getting smaller and smaller as the processing evolves. And finally, here's our fourth iteration, third to fourth, third to fourth. And just to summarize, we plotted up in histogram mode the distribution of both the shot and receiver scalars as a function of increasing iteration number. And satisfyingly so, you observe that in the initial iteration, there's a lot of variation. And as the stuff evolves, as the processing evolves, you get a tighter and tighter cluster. So it's in keeping with how it's in keeping with your expectation. And so we analyze these things. A similar analysis can be performed in the context of phase variation. So what do we do in processing AVO compliant to address phase of the wavelets? Well, we've got deconvolution is really our workhorse, and what we're doing here is we're measuring the phase of the embedded wavelets on your seismic and showing the source and receiver phase only of these wavelets. The way we're able to measure this is something Peter's going to get into detail in a few minutes. But for now, just suffice it to know that we measured the phase, the source-consistent part of the phase of the embedded wavelets before decon, and got quite a bit of spread in the phase, meaning that there's all sorts of lateral phase variations in the wavelets. And similarly for the receivers. We do a first pass of decon, and you notice that the histogram shows a more tightly clustered distribution. So that means we're removing a lot of these lateral phase distortions. But things are still not perfect. Now, the reason we do a second pass of decon is because we think the algorithmic assumptions of decon are better fulfilled when we operate on noise-free data. So this second pass occurs much later on in the flow when we beat down a lot of noise, and most satisfyingly, you see that the phase variation is now quite minimized. So the last thing I want to show before I turn things over to Peter, Lee Hunt studied some of these effects independently on some of our processing, and he had a synthetic, he had a lot of well control. He did elastic modeling to get the gold standard answer at his well location. And he basically compared a gather at the same location, both at a very immature stage of the processing, basically raw data where we'd only applied inverse Q and ground wave suppression. And he watched the thing evolve at different stages, and I'm just showing the first raw product and the final product, but by the time we get to 5D and PSTM, there's much more similarity. And just more quantitatively, as you go from raw on the right to final, he measured the amplitudes in a window. And for the synthetic, which I'm showing in red, he knows the right answer. So he's just plotting the same synthetic amplitudes, the known answer, same in both the final and raw panes on the left and right, so that these two red curves are identical, just for a reference. The important thing to note is the raw measurements, so that ground level attenuation only example, there's a huge spread in those orangey yellow points, but by the time we evolve our processing to final, we get these blue points, and they're much closer to the synthetic. So there's method behind all this madness, this hard-fought AVO compliant processing. Here it is showing a final result in a well-calibrated study, and it's actually doing some useful things. So I'm going to pass things over to Peter. He's going to talk in particular about some of these algorithms.
So Mike said I was going to go into details. Of course, there's not a lot of time for details here, but the next few topics are items that I've been personally involved in. So first of all, this surface consistent scaling. This is a topic which I first became involved in several years ago when I noticed that really very often, despite all our best efforts, there were really obvious problems coming out in our final AVO compliant, so-called AVO compliant data. Really obvious lateral changes in amplitude on the survey. And they seem to characteristically be tied in with variable amounts of noise. And we were using kind of standard Tanner et al. Type algorithms that have been popular since the 70s. So it was a workhorse. And with all those type of surface consistent processes, you were able to beat down the noise and design your operators based on the data offline, but apply it to online. But regardless of how much we did that, how much conditioning, we still didn't get satisfactory answers. So that's what prompted this particular work, where we, instead of letting noise bias the results of our signal magnitude, we use basically stacking processes, a couple of different methods we have now, in order to beat down the signal-to-noise ratio over the entire frequency range. So just to explain more, this is the type of kind of obvious problems that we noticed in a lot of our data. These are common receiver stacks over one particular receiver line in a 3D survey from southern Oklahoma. This vertical banding in here is indicative that there's obvious amplitude variations from receiver to receiver. And this passes on through to the CDP stack. At first I thought this was a bug in the code, but no, in fact the code's working just fine. The problem is that the code is designed to balance out the amplitudes of the total energy in the traces rather than just the signal. So once we take away that bias on the noise, we're able to remove almost entirely that straightness. And as I say, we have a couple methods to do that now, this is pretty much a routine process in our AVO compliant processing. This is the effect on the stack in one location. The characteristic dimming here indicates problems in the AVO processing. And the only difference between these two is this unbiased AVO compliant scaling step. So as you can see, the background signal now on these reflections is much more consistent than before. And of course, the noise has been blown up. The noise is the source of the problem to begin with. So this processing isn't finished with. We need to now do more noise attenuation. So we're starting to move this process, this unbiased process, earlier and earlier in the processing flow, so that in fact the noise ends up getting blown up more, essentially, because we're scaling our data based on signal rather than signal plus noise. Just one more example. This one is from the Loyal 3C3D in Oklahoma. You'll see more of this data set through the afternoon here. So this is just before and after. And as you can see, with the proper scaling, you get much more consistent lateral variations in the amplitudes. And notice you're able to resolve long wavelength changes in amplitude changes, which is really nice out of this algorithm. That's, in fact, I think the main advantage of that algorithm. Going on to the phase issues now. Instead of being quite obvious as the amplitude problems were, the phase issues are much more subtle and harder to see. In fact, I think you really do need to look for them if you're going to find them in much of our data. So this example is probably hard to see, maybe even from the front of the room. The difference is in the quality of the stacking between the second and third results. So this is just a synthetic example where supposedly after decon we've come out with both errors in statics and in phase. So if you look closely enough, there's little phase rotations within each one of the wavelets. In our standard processing flow, we go through residual statics to line up peaks and peaks, peaks with peaks and troughs with troughs. So you get a nice coherent looking result, whether this is a gather or a stack, you get a nice result. But the trouble is that the phase errors still exist in the data. And you actually need to look for them. The statics tries to mask the phase errors. It's because there's this anti-correlation going on between phase and statics, which always tends to help us get more coherent results, but not necessarily the best. So to try to explain that statement, suppose you've got an ideal zero phase wavelet here. This is your actual correct answer after decon, for example. But you've got both a negative phase rotation and a static on your data. So the perfect solution would be at the peak of this stack power, and this would be the stack power of one particular shot, for example. But you've got both a phase and static for that traces in that shot coming up. So in our residual statics, we assume there's no phase errors, so you just move horizontally in this diagram to the local maximum. That comes up with a static shift, which lines up the peak with the peak in this segment. But as you can see, if we apply both a static and a phase rotation that are in fact anti-correlated with each other, we get to the correct answer, and we end up with a zero phase wave. So that's a basic concept for explaining why we really haven't uncovered a lot of phase errors up until now before we actually looked at it. This process of surface consistent phase and statics resolved simultaneously is produces results that are like this. So this is a heavy oil example. The Devonians, about in here. This zoom in here shows typical results. So it's sort of like an additional residual statics correction. It might not look like a huge amount, but when you're doing AVO processing, details are very important, especially on the final gathers where you're doing AVO analysis. If we look at these 4 different CDP gathers before and after, you see this slight improvement in the coherency of the phase and the wavelets overall. These plots up here are phase and static for each individual trace, and as you can see, it shows this anti-correlation. When one goes up, the other goes down. So this is a slight phase consistency improvement, and that follows through into the AVO attributes. So just an example of the 2 simplest AVO attributes here, just intersecting gradient stacks derived from the data. So this is before and after, before and after. And within the highlighted zones here, you can see some improvement in terms of coherency of phase, consistency of wavelength. So these could, in fact, have quite an impact on your final inversion results, for example. Additional evidence of the reality of these phase errors in the data comes from, for example, this type of plot where we see that the receiver consistent phase correlates amazingly well in this situation with surface elevation, and presumably because the receivers were responding differently in the to different elevations, saturation levels, or whatever in the soil. And as I say, we characteristically observe this anti-correlation of statics and phase on both the source and the receiver side as additional evidence that what we're doing here is correct. So I'm the 3C guy here primarily, so I'm going to talk about some multi-component data here and how our AVO processing basically carries over directly into the converter world without a whole lot of variation, except of course that we start out at least with 2 horizontal components, and you have to be consistent between the 2 in all processing steps. So, for example, whenever you're driving statics, wavelets, amplitudes, you need to be able to ensure that what you're doing to one component is the same as on the other. So we'll often design on the radial and apply to both the radial and the transverse, for example. So just some examples here of ground roll attenuation, first of all. This is just a before and after plot, similar to the type that Mike was showing. The noise attenuation, unfortunately, tends to always be a bit tougher on the PS data, partly just because there's more of it compared to the signal level. The signal levels are a little lower than on the P wave. And also, of course, the bandwidth of the PS data tends to be also lower. So, for example, the ground roll frequencies tend to overlap more on the PS side than on the P wave side. So we need to typically work a little harder on the noise side. So this is just another example of the noise attenuation in this controlled FK post-TSTM process. And more examples, the unbiased surface consistent scaling again. Because there's more noise, the examples on PS data sometimes are more spectacular than on the P-wave side. So this is the original radial receiver stack and shot stack, and after one pass of this surface consistent scaling, unbiased, and then a second one. So you can see how we gradually, iteratively get to a better and better solution. And then finally, just to show off a bit, I guess, this example from Oklahoma, the Loyal 3C, 3D. This is just one inline from the P wave, showing the average amplitude spectrum over this entire section here, the P wave and the PS. We're really quite pleased with how well this has worked out. as you can see, a surprisingly good correspondence in the amplitude inspections. Believe me, it doesn't always work out this way, but we're always very pleased when it does. And in fact, when you go and stare at this data, there's some aspects of the PS data which we tend to like more than the PS, but the P-wave data. Right? So there's going to be more about multi-component in my second talk, but we're going to finish AVO first.
So I'm going to move into Azimuthal processing, as Peter mentioned. And the other thing, not only was he showing off with his really nice frequency content on that oil example, he was showing off because he was using both hands for a second laser pointer, and I didn't have the coordination to do that. I didn't think, so I'm going to try it now. So, okay. So I'm talking now for the next few minutes about very careful azimuth preserving processing. And really the workhorse behind this azimuth preserving processing is 5D interpolation. 5D interpolation, when you cast the data onto well-sampled azimuth sectors, it basically enables processing that preserves azimuthally varying features. And the features that we typically are concerned with are velocities and amplitudes. And it follows that this kind of careful azimuth compliant, if I may use that term, that careful azimuth compliant processing is required for downstream processes like azimuthal velocity work and azimuth work for PP data. So I thought it would be instructive to just show the algorithmic action of 5D interpolation before we get into things. So this is really a talk about advances. It's not a tutorial style presentation, but I do feel there's not a lot of good tutorial demonstrations of what 5D interpolation is doing. So bear with me for just a couple minutes here. So I took a CMP from a real Western Canada survey, fairly well sampled, regularly sampled, an orthogonal survey. I'm focusing on just one CMP here, and I decided to take all 20 traces, it was 20-fold data, and I mapped them onto this coordinate system here that's just displaying inline and cross-line offset. So basically I took each trace and I applied a pure translation so that the source for each trace coincided with the origin of this plotting system, and then I drew in the receiver location, and that became my plotting point. So that's trace 1, and of course the distance there, the polar distance, is the source receiver offset, and the angle with the x-axis is source receiver azimuth. No surprises there. I repeat for the second trace in this fixed CMP, and so on, and I've got all 20 traces inscribed here. Okay, that's all good and well. What about 5D interpolation? I'm now going to superimpose a typical 5D computational grid. So this grid here you see was chosen very carefully. The offset sampling, which corresponds to the number of these concentric circles you see, it was chosen based on what we really used according to metrics which are beyond the scope of this presentation, but we chose realistic parameters, and that controls the number of these concentric circles. The azimuth sampling, we chose 6 azimuths from 0 to 180 degrees, and those 6 azimuths are manifest in these 6 pi wedges you see before you. So there's the computational grid that's basically driving the 5D process in many ways. And what needs to happen at the initialization phase of the algorithm is these 20 traces, first of all, get gridded. They get mapped to the center of these little wedges. So there's trace 1, there's his original location, there he is being moved to bin center, trace 2, trace 3, and so forth. I'll repeat it for all 20 traces, so they've now been gridded. And just to emphasize the gridding, I've in this yellow color, brown hollow color, I'm showing the original trace locations. So the last thing I want to say before I show the algorithmic action of 5D, I want to emphasize the 2 near offset classes, so these first 2 concentric circles. Does everybody see there are no traces there? No input traces. And that's actually a problem when it comes to the 5D interpolated output. In fact, the same problem is manifested in pre-stack time migration. If you ignore 5D, the near offset classes are not typically well sampled. So all I want to say on this topic is we're looking into new ways to grid the data to avoid this problem in 5D interpolation. So 5D interpolation, like magic, presto, fills in all these holes. You get this wonderfully, magically sampled set of traces at this fixed CMP, all the offsets and azimuths populated. And we call this subsurface grid output for what that's worth. And I want to emphasize that I'm focusing on one particular CMP here, but behind the scenes, this magical algorithm is filling things in for all the CMPs. And Daniel Trad, who's the inventor of 5D interpolation, he himself calls this subsurface grid output great sampling. And so we like to use this domain. It turns out that if you look at any one of these particular little wedgies, like this one in yellow, where the offset in azimuth is very well localized, that's a great approximation to what I would call a pure common offset vector, COV, or equivalently a pure common offset in azimuth. So if you look not just at one CMP now, but the totality of all the CMPs for this fixed COV, it's this volume that migration theory tells us migration loves. Migration does a great job of migrating these individual COVs. So when we go to do our azimuth preserving migration, which is really the workhorse for all this azimuth dedicated processing I'm about to tell you about, it works as follows. Original acquisition, do 5D interpolation, we take each one of these COVs and we migrate them independently. And then we get this naturally an output that preserves offsets and azimuths. So what about this azimuth sensitive or azimuth independent processing? Okay, well there were a couple of different applications. First of all, there's azimuth-oriented noise attenuation. And really the sub-applications of interest are linear noise attenuation and multiple noise attenuation. So the idea here is we process the noise within each azimuth sector independently. And conventional tools like FK filtering, radon for either linear noise attenuation or multiple remover, they actually work quite well because 5D interpolation has done this heavy lifting behind the scenes and given us very well sampled azimuth chunks of data, if you will. So it opens the gateway to allow use of conventional tools. So that's what we're going to study in the next few slides. And the other big application is to apply HTI-style residual move-out correction. So those are the azimuth-sensitive processing elements. So let's look at noise attenuation. We'll look at a noisy COCA display. This is after migration. Probably many, if not most of you, know what a COCA is, but for those of you who are not familiar with the construct, this is a single CMP after this azimuth-sectored migration, which of course came after 5D interpolation. And what we do to order the data, the offset is the primary sort key. So that is to say that in a gross sense, from left to right, the offsets are increasing. Azimuth is the secondary sort key. So that means that any 6 adjacent traces have essentially the same offset, but the azimuth scroll between 0 and 180. So with this particular domain chosen, you get that classic sinusoidal wobble and travel times, which is often associated with HTI and isotropy. So that's why we like looking at this domain. So I could equally have taken my data, though, and I could have put them in what I call CACO order. So I could have made azimuth the primary sort key. So here you're seeing 4 of these sub-azimuth chunks, and the offset's the secondary sort key, which means that as my laser pointer is scrolling, I'm exploring all the offsets for fixed azimuth. And each of these, well, there's 6 in total, all those gathers look like good old CMP gathers. So what we can do is take each of these individually, operate on them piecewise, and in this case do linear noise attenuation using the same controlled FK algorithm that Peter described in his talk. So there's one of these CACOs. This is 1 CMP's worth of data, just looking at 4 out of 6 azimuths, just for screen real estate reasons, before and after this linear noise attenuation, before, after, before, after. And if you view the same data in COCA mode, there's the before and there's the after, before, after. Why am I bothering showing all this? That subtle azimuthal effects in travel time and amplitude are preserved through this process, before, after, before, after. So the last thing I want to leave you with before we go to questions is that second cog of our azimuth dedicated processing, and it's this notion of residual HTI correction. So in some applications, you may not like this sinusoidal wobble. You may want to flatten it. For instance, if you're going to do azimuthal AVO work, or get improved focusing when you stack these gathers together. So we have a technique for doing this. To be totally honest, we're adopting a simplified approach relative to some other providers. Other providers have talked about orthorhombic time imaging. We view simplicity as something desirable here. Instead of an orthorhombic migration, we'll apply a standard VTI compliant pre-stack time migration and then operate on the gathers with this COCA notion in mind, we'll operate on those gathers after the fact, after migration, to just flatten. And the way we do it is to employ the HTI NMO equation in conjunction with this flow. Simple flow, pick horizons on a stack, input your gathers, you compute the delta t's that describe that sinusoidal wobble, and then you do a least squares fit to a very well-known HTI NMO equation to get effective, these are RMS style parameters, V fast, V slow, and beta at every horizon for all CMPs, do a bit of temporal and spatial interpolation, and then apply the resulting correction to the data. And here's how it plays out. On the left is a migrated gather in COCA mode with all the azimuths preserved, and there you see your classic sinusoidal wobble. And now we flatten that sinusoidal wobble based on this HTI NMO equation and get hopefully a decent result. So I think that's the last thing I wanted to say in terms of detailed algorithm discussion, but I wanted to close off by echoing something Peter said. So it's essentially, we all know how to make nice, pretty PowerPoints in this industry. We typically choose our really good data examples, and to some degree, guilty is charged here. I think you've seen some pretty compelling, neat examples. Our tools work fairly well in many cases, but the reality is, and many of you know this, the tools don't always work well. In such cases, what we pledge to you is absolute honesty about how our algorithms work, a really good understanding of fundamentals, access to what we think are industry-leading tools, and hopefully pragmatic solutions to help you mitigate whatever problems persist, because sometimes you do get remnant noise problems and amplitude striping and so forth. So thank you very much for your attention on this rather dry but critically important topic.